My name is Monica Gupta. I'm a principal engineer at Intel, and I've been working with Intel for over a decade now. I'm part of the team that works very closely with our great partner Microsoft. And as part of my role, we work on innovating, defining, and bringing next generation processor technologies to life in Windows. This work enables Intel processors run best with Windows, and Windows run best on Intel processors. During my tenure at Intel, I've had the opportunity of bringing many new technologies to life, since the ideation to making it a reality. One such technology is hybrid architecture, and today we'll be presenting on hybrid architecture, scheduling with Intel Thread Director technology, and specifically talk about our new processor Lunar Lake. Windows enabling done to take maximum advantage of Lunar Lake architecture and what software developers can do to take maximum advantage of this new architecture. This session will be jointly presented with one of our Microsoft partners, Tapan Ansal, who has been the key developer on the Lunar Lake hybrid changes in Windows. Hybrid architecture integrated two core families for breakthrough performance, efficiency, and flexibility. P cores are optimized for best performance, and E cores are optimized for scaling highly threaded applications. Intel is not following the cookie cutter approach. Some usages like gaming really need the best performance of P cores, and some workloads really scale well with increased core count. Did you know, leveraging E cores, we can place 4 E cores in approximately the same space as one P core, providing a highly efficient multi-threaded system. And this design is extensible and gives us the flexibility to add or subtract certain types of cores in the future to meet changing needs. As is pretty evident with multiple generations of hybrid architecture in Alder Lake, Raptor Lake, Meteor Lake, and now Lunar Lake. What's new with Lunar Lake hybrid architecture? Lunar Lake provides the best mobile experience by leveraging a low-power island architecture. Low-power island allows us to power off more of SoC infrastructure even when one or more cores are active. What that means is we are still computing, but with better energy efficiency and a much lower power cost. Alder Lake was the first mainstream hybrid architecture. On Alder Lake and Raptor Lake, our goal was to provide maximum and consistent performance. Performant cores were used first, and when they're busy, then E cores were optimally used for maximum multi-threaded performance. Meteor Lake further introduced disaggregated die architecture for improved battery life. In this, it used an SoC tile with 2 low-power E cores that can execute low utilization, low power usages like video playback at much lower cost. Once the work does not fit on low power E cores, the work moves to compute tile, leveraging efficient and performant cores on compute tile based on the demand of the work. On Lunar Lake with low power island, the concept is similar to SoC tile, where a lot of infrastructure can be powered off when one or more cores are active. Lunar Lake has 4 high-performing E cores on that low-power island, where you can execute high utilization scenarios at low power cost, meaning teams conferencing, streaming at world-class battery life. Once the work does not fit on low-power island, it uses other P cores and low-power island E cores based on the demand of the work. The scheduling decisions over Intel hybrid processor generations is brought about with a hardware-software collaborative feature called hardware-guided scheduling, also known as Intel Thread Director technology. The feature provides hints or guidance into Windows scheduling and parking engine to place right thread on the right core. Intel's Thread Director technology. On hybrid architecture, this technology provides dynamic hints from hardware to the operating system for making optimal scheduling decision. What it does is it exposes runtime performance and efficiency capabilities of different cores to the OS based off power and thermal constraints on the system. Say user is playing a game, making graphics core active enough to require additional power budget from SoC. An E-core may become the most performant core, or operating on limited set of cores may provide best system performance. In these dynamic conditions, hardware would interrupt the OS with updated capabilities, and OS would consume the information to move threads on the most optimal set of cores. Performance and efficiency capabilities are used by scheduler and parking engine to guide high-demand foreground to performant cores and low-power foreground work to efficient cores and background work to efficient cores. And the good news is this capability is even available as part of Windows 10. Think about Thread Director as a layer between cores and OS. What are the thread classes in this Thread Director technology? Based on thread instruction set mix, Thread Director technology bucketizes threads into different classes. There are thread classes that can gain much more performance than P cores, and there are classes that may not gain as much performance from P cores compared to the E cores. With this distinction, operating system can prioritize threads that gain much more performance for P cores versus the thread that may not gain as much. Leveraging thread classes from hardware to prioritize threads between hardware and software is available as starting with Windows 11. Thread Director in Lunar Lake is even more optimized and made more intelligent to provide optimal scheduling guidance to OS. Thread Director technology provides special containment hints to guide OS towards that low power island. Lunar Lake adjusted the Thread Director classification with the evolution of new PNE core microarchitecture. Let's look at scheduling with the help of an animation, followed by containment to help describe scheduling on this low power island. On Windows, Parking Engine acts as an assist to the scheduler. Heteroparking uses hardware efficiency hints to start work on E-cores. And when thread concurrency increases, it expands to additional cores. This expansion is done based on the hardware-guided efficiency capability order. This allows us to achieve maximum battery life, leveraging the efficient cores on the system first when the demand is low. Once the demand increases, Windows Heteroparking Engine uses hardware performance hints to make performant cores available for the scheduler, providing maximum performance and responsiveness. Containment is a new hardware-software collaborative feature in Windows Heteroparking Engine. It helps Windows determine low power island on Lunar Lake platforms as efficiency zone. When efficiency zone is most efficient from Intel's thread director's hints, Parking Engine applies additional pressure on foreground threads to run on that low power island and avoids moving to other cores for short burst in demand. Remember, E-cores on low power island provide high performance and are enough to meet the needs of that burst in demand. So at this point, there is no need to use the other cores that sit outside low power island. In addition, when foreground work fits on low power island, Parking Engine makes best effort to keep background activity serialized on low power island. With these innovations in Windows Heteroparking Engine, containment feature has been crucial to ensure maximum advantage of low power island on Lunar Lake, providing best-in-class energy efficiency and battery life. And once hardware or OS determine that low power island is not enough to meet the demand, it starts utilizing hybrid zone or all cores for maximum peak performance and maximum multi-threaded performance. Same as previous generations of hybrid architecture, when we have highly concurrent foreground and background activity, Windows consolidates background work on efficient cores to ensure that it does not interfere with foreground work running on performant cores. Scheduling decisions are dynamic in nature and dependent on runtime hints from hardware based on the underlying architecture. While there's nothing an application developer really needs to do to take advantage of this hardware-software collaborative scheduling decisions, there are some things that software community can do to be a good citizen on hybrid platforms. Let us now hear from Tapan from Microsoft on how software developers can influence hybrid scheduling.
Thank you, Monica. Hello, everyone. I'm Tapan Ansal, and I work in the Windows Core OS organization. My team is responsible for designing and developing power management solution across all Windows-based queues. To enable Windows on Intel processors, we work closely with Monica and Monica's team to optimize new Intel platform for their silicon design, achieving better power and performance. This collaboration between Intel and Microsoft is crucial for our success. So now let's get back to the agenda. So let's first talk about how application writers can contribute towards optimal hybrid scheduling. So let's delve into some practical example how EcoQuas can be utilized in IT and enterprise settings. So there are certain cases where it can be utilized. So one of such example is background services. EcoQuas is perfect for background tasks that don't require high performance, such as system updates, file indexing, and data synchronization. By opting into EcoQuas, these services can operate more efficiently, reducing power consumption and extending battery life. Another example can be administrative and business critical traffic. So, in these industries with strict regulations, it is essential to separate administrative traffic from business critical traffic. EcoQuas can manage non critical administrative tasks like hardware and software inventory reporting, which don't need to be real time. Another example can be occasionally connected devices. For devices that are not always connected to the network, EcoQuas help manage traffic and ensure essential tasks are performed efficiently without draining the battery. Windows provide APIs for app developers to give such hints to the operating system. Power throttling API is a mechanism that application writers can use to influence Windows scheduling decisions on hybrid system. It helps improve Windows' understanding of performance critical or non critical threads by opting in and out of power throttling. This in turn allows Windows to optimally schedule tasks on performance or efficient core. Opt in into power throttling. So, this is ideal for energy conscious tasks. By opting in, we can achieve enhanced efficiency, helping manage power consumption effectively. It also allows for smart resource allocation, as application can provide hints to the operating system about their power requirement. This leads to improved user experience, balancing performance and power consumption for smoother operation. And opt out in power throttling. For performance critical tasks, sometimes it is necessary to opt out. However, this should be used sparingly as it can significantly impact battery life. These APIs are have been available since Windows 10. So what are those APIs? So as you can see, we have the API where we have power throttling state, which is a structure, and you need to provide the version of your power throttling current version, and then you one application writer can use the control mask and the state mask to tell operating system that hey, my application can throttle for speed execution, and in that way, once you call this API set process information, by calling your process handle with get current process and passing this structure, you are actually indicating that you want throttling on the execution speed and giving a hint to the operating system that we can classify this process or thread as EcoQuas and then optimally schedule this onto proper efficient core. Now let's delve into affinity and avoid affinity. So why affinity can be a bit of troublemaker when it comes to optimal scheduling? Affinity disrupts the scheduler ability to make the best decision about where to run work. If you are an app developer aiming for maximum performance, leveraging power throttling API, which we discussed in the last slide, is the way to go. This allows you to guide the usage of performance and efficient code effectively. For instance, if you want to run your application on most performant core, using the power throttling API is your best bet. While we generally don't see affinity used much in the software, there are some exceptions. On servers, affinity might be used for resources that are close to the memory. However, on the client system, using affinity can cause issues, especially impacting battery life. So when containment feature is unable to confine work on a specific zone, particularly under low workload, processes or threads, affinity to other zone can significantly reduce the advantage of containment. Traditionally, affinity has been used to run on same or mutually exclusive processor. In these scenario, threads can use CPU sets API instead. This approach allows for better resource management and avoid pitfalls of affinity. So let's take an example of CPU sets. So for CPU set, first of all, you can call this API get system CPU set information to get all the CPU set available for this particular system. And then let's take an example for your process. You want to set the first CPU set. So you will pass the array with first CPU set. And in that case, all the thread in this process without any other explicit assignment will be affinitized to first set. But let's say you want that some threads in this process affinitize to a set one. In that case, you can set the thread select CPU set, get that thread handle, and then instead of index 0, you will pass the index 1, and then this thread in this process will be affinitized to CPU set 1. So using CPU set is the best way in case your application really want to leverage affinity to specific CPUs. So OS actually recommend to use this mechanism than hard affinity to a specific CPU. So now let's talk about multimedia. We need to understand the multimedia. For that, we need to first understand the media foundation. So media foundation is multimedia framework developed by Microsoft that handles audio and video content across different devices and application. It supports wide range of codecs and formats, enabling high quality playback, streaming, and recording. It also includes features like DRM, that is digital right management, to protect the content from unauthorized use. Now let's talk about MMCOS. MMCOS enhance multimedia performance by prioritizing tasks and managing system resources effectively. Here are some key benefits. So benefit number one, prioritization of multimedia task. MMCOS ensure multimedia application get necessary CPU and memory resources, reducing latency and improving user experience. Efficient resource management. It balances performance and energy efficiency. This is crucial for device with limited battery life. Selective throttling. So selective MMCOS can selectively throttle media batching, similar to how background application manager, aka BAM, throttle background application, and maintaining the performance while optimizing power usage. And the another advantage of MMCOS is improved scheduling. MMCOS works with system scheduler to ensure timely execution of multimedia tasks, reducing performance issues due to resource contention. By implementing these strategies, MMCOS provide a better experience for multimedia application, ensuring smooth playbacks, reduced latency, and efficient resource usage. Finally, let's discuss about some recommendations for app developers. The general recommendation is to leverage the OS media support. This approach take full advantage of various features designed to enhance both power efficiency and playback robustness and the quality. By relying on the OS media support, developer can ensure their application benefit from the latest optimization and improvement. One key aspect is to avoid thread affinitization, which we discussed in the last slide as well. This strategy maximizes concurrency, allowing the kernel to schedule work execution in the most power optimal way. By not restricting thread to a specific core, the system can better manage resources and improve overall performance. Looking ahead, Future improvements will focus on enhanced scheduling and power management across CPU, GPU, NPU, audio, camera, and display workload, further optimizing the performance and the efficiency. So we have discussed a lot of recommendations for app developers. Now let's address some key strategies for device driver developers as well. One crucial method for optimizing performance on Windows is through optimal interrupt steering. Windows default interrupt steering algorithm aims to improve unnecessary wake-ups of idle code and avoids interfering with the performance code when they are not needed, particularly on the hybrid platforms. This strategy is essential for maintaining both performance and power efficiency. This algorithm operates in tandem with core parking engine, ensuring that code generating the interrupt can also service it. Theref- Thereby, it reduces the latency and avoid negative impacts on the performance or battery life. The advantage of this system lies in its implementation via our policy machine default uh, service. For device driver developer, it is advisable to set timers for longer period whenever possible, unless there is a compelling reason not to do so. Additionally, avoid using high resolution timer unless necessary, as they can lead to higher power consumption and decreased system efficiency. By implementing these strategies, device driver developers can ensure their driver function efficiently, leveraging Windows' advanced scheduling and power management features to their fullest potential. Lastly, driver developers should ensure that interrupt policy with explicit processor affinities are not set, as these can disrupt optimal interrupt steering. And this is an example where it is advisable to not use such APIs. With this, back to Monica to reinforce the call for actions.
Thank you, Tapan, for great tips. To summarize, avoid affinity and when needed, leverage power throttling APIs or CPU set APIs. For media applications, take advantage of Windows Media Framework. And for driver developers, use default interrupt steering policy and avoid using high resolution timers. Thank you, everybody.